All right, guys, welcome to our lesson now on gases, new unit. You guys, I'm covering a lot here, some of which, let me fix this. Generally, I introduced gases the previous year in honors or regular chemistry, but because of COVID, we got ended early. So a lot of you guys haven't had this. So I might be going a little quick, but that's where you'll have opportunity to ask me when in our live session for help on some subsequent problems. You know what, just for sake of time, I'm just gonna go quick. So we're talking about gases, right? They expand to fill their containers. They're highly compressible because the molecules are spread out so you can compress gases, and they have extremely low densities. That means the weight or the mass compared to the volume is very light, very minimal. So when we're talking about gases, we often talk about pressure. Pressure is defined as the force per unit area, okay? So it says the atmospheric pressure is the weight of the air per unit of area. So what we would take, for example, is 1 square meter, and the weight or the force that air is applying to that area would determine the pressure of the gas. Here are some different units we use for pressure. It's not purple. We have pascals, we have bar. Ones that we prefer are these ones here. Here are 2 millimeters of mercury and torr. Torr comes from an Italian who worked with this, Torricelli. Millimeters of mercury, because we can have what's called a barometer. You guys see here, this is a evacuated tube. There's mercury in it. One might think, and then this is an open pool of mercury. Why doesn't the mercury just fall due to gravity? Well, atmospheric pressure, the air has air molecules that are moving and they're exerting a pressure, and that pressure that the air is exerting is elevating this mercury. So we could measure the length of the mercury, and then that could be a measure of the atmospheric pressure. Wouldn't you guys agree? The higher the column of mercury the air can support, the higher the atmospheric pressure, and then the lower. So we can actually measure the length of that mercury and measure air pressure in millimeters of mercury. Here's some other units that we should be familiar with. So if it can support a column of mercury 760 millimeters high, we call that standard pressure. We can call that 760 torr. You guys see those are just 2 different ways to say the same thing. And the equivalent in atmospheres, ATM is short for atmospheres, is 1 atmosphere. So this is what we would call standard atmospheric pressure at 0 degrees Celsius. And at sea level, that is the pressure that air will exert. It will hold up a column of mercury 760 millimeters of mercury high. Okay, I'm going to, I guess we'll show this. So let's say in a manometer, let's say we have a gas in this tube here, and it's in this open tube, right? So we open this up, and then we have some mercury here. Well, you guys can imagine the atmospheric pressure is pushing this way. The gas molecules are moving; they're exerting a pressure this way. If these 2 were equal, if the pressure of the gas was equal to the atmospheric pressure, wouldn't the column of mercury be the same level, right? But the fact that the mercury is pushed up this way, what does that tell you about the pressure of the gas? It must be greater than the atmospheric pressure. And so what is the pressure of the gas? We can say the pressure of the gas, wouldn't you guys agree? It's going to be equal to the atmospheric pressure plus whatever the weight or the pressure that this extra column of mercury is exerting, okay? Like I say, guys, I'm going a little fast. It's because we didn't have the prior lesson, but we'll try to do the best we can. So standard pressure is 1 atmosphere. We can call it 760 torr, 760 millimeters of mercury. If you're taking a physics class, this would probably be the preferable units that we would use. So how are pressure and volume related? Okay, so there's various factors. When we talk about a sample of gas, just think about a balloon. So pressure and volume, how are they related? Well, if you guys just look at the balloon, right, think about it. If there's a certain amount of gas in there, if I reduce the volume, you guys can imagine, what do you guys think I'm experiencing right now? When you guys imagine as I'm decreasing the volume, you can feel a resistance. What's happening to the pressure? So as the volume's decreasing, the pressure is increasing. We call that an inverse relationship. Volume is inversely proportional to the pressure. That was Boyle's law. A graph, so what would that look like? So if we were to graph that, here, we'll just show that. Here, if you were to graph pressure versus volume, so if we have pressure here, volume here, you guys will see as pressure increases, it would look like this curve right here. At a higher pressure, it equates to a lower volume. But then look, as the volume increases, well, I actually prefer it the other way around. I use like volume down here and pressure here. But nonetheless, you can see a low pressure corresponds with a high volume, and a low volume corresponds with a high pressure, inversely proportional. So what the reality is, if you take the pressure times the volume for a sample of gas, you will always get a small k that's a constant. So for example, look, so let's say we have a certain volume. Let's decrease the volume by half. How would I show that? When I show that dividing it by 2, right? So let's say I went from 2 liters to 1 liter, right? Well, what happens to the pressure? They're inversely proportional. If the volume's cut in half, the pressure doubles. Now you guys look, what happens to the 2's? They cancel out. So regardless, the product of these will always equal a constant. That's what that's showing. How are volume and temperature related? Okay? Well, you guys can probably just think about it. What do you guys think is going to happen if you heated this up, right? Wouldn't you guys agree? Aren't the molecules going to be moving faster? And if they're moving faster, let's just say if we're going to keep the pressure constant, okay? So what's the only way that the pressure of the gas will stay constant? If the molecules are moving faster, what has to happen to the volume? What do you guys expect when you put this in a hotter room? What's going to happen to the balloon? It's going to expand. So as temperature increases, volume increases, and you might also predict as temperature decreases, volume decreases, we would say that that is a directly proportional relationship. So what would the graph of that, of volume versus temperature, look like? Oh, before that. So if 2 things are directly proportional, then their quotient will always equal constant. Think about this, guys. So once again, if I double the temperature, if they're directly proportional, if I double the temperature, what happens to the volume? Doesn't the volume double? And you guys, look what happens. Those cancel out. And what's going to happen is we're going to get the same value every time. So the quotient of 2 things that are directly proportional always equal a constant. If you were to graph this, it would look like a straight line. Wouldn't you guys agree? See, as the temperature increases, the volume increases. Okay. And so then what we can do is we can place these together. Oh, before that, you know what? We can put these together. So look, P times V equals K, and V over T equals K. So if we put these things together, if we could kind of combine all 3 factors together, what we can get is P times V over T is equal to K. And ultimately, this is going to lead us to what's called the combined gas law, guys. You want to write this down. So if it's always equal to a constant, if I take my pressure, volume, and my temperature under one set of conditions, and let's say we change the conditions, let's say there's a certain pressure, volume, and temperature that this sample of gas has, then let's say I change the temperature. Well, you guys know if I change the temperature, that's going to have an effect on the pressure and the volume. Well, the new pressure, volume, and temperature we call P2, V2, and T2. But see, because the relationship here always equals a constant, we can set these equal to each other. This is called the combined gas law. Write that down, guys. Combined gas law. Okay. Now there's one other factor, however, that we have to include. There's actually 4 factors when we're talking about a gas. Not just the pressure, not just the volume, not just the temperature, which we've included here, but we also have to include how much gas we have, and we would indicate that with the number of moles of gas. So the question I have here is, how are volume and pressure related to the moles of gas? What do you guys think? What do you guys think? Let's say we have, we put more molecules, gas molecules in here, so we increase the moles. What effects that can have on the volume and the pressure? The volume of the gas at constant temperature and pressure is directly proportional to the number of moles of the gas. So now we're looking at the volume. So what we can say here is, guys, I don't know if you guys can see this. I would write that down. The volume and the number of moles of gas are proportional. Once again, what does that mean? If we double the number of moles of gas, so if I double the number of moles of gas, assuming we keep the pressure and temperature constant, what's going to happen to the volume? That's going to double. We can see the quotient always equals the same value. So, if that's the case, here's what we can do. Oh, so then ultimately, let me see what you guys are looking at. Okay, so now we want to try to incorporate N into this right here. So look at that. So we know, think about what we had here. The volume and the number of moles are directly proportional. How can we put that in here? Well, that's what we'll do. We'll put it under. And now you guys, this is what's important about this, is this actually incorporates all 4 factors that affect the gas. So this is a very important equation here. And it's so important that This K, we're going to actually give it a special designation. We're going to actually call that an R. That is our universal gas law constant. And what makes that particularly significant is that it incorporates all four factors that can potentially affect a gas. That's why we don't just call it a small k annual constant, it's R. This is the universal gas law constant. And you guys write this down, because I don't know if I'm putting it on a slide. It's equal to 0.0821 liter atmospheres per mole Kelvin. You guys see where all those units come from? Liters from volume, atmospheres from pressure, the K for temperature, because temperature has to be measured in Kelvin. By the way, guys, that's here as well. So what we're going to do is just rearrange this. And if you do it algebraically, this is the form that we typically use. PV equals nRT. This is called the universal gas law. Okay. So, you guys, here is, you know what, I think I just wanted to stop there. I was going to do some more, but I think I've already bombarded you guys with a lot. So ultimately, guys, the summary of this lesson is we ultimately arrive at two gas equations. So when you guys encounter a gas problem, what you just need to do then is decide which one am I going to use. So the question is, how are you going to know which one to use? Well, if you guys look here, the big thing with this is here you have two sets of conditions. So if you encounter a problem in which you have a sample of gas and then one of the factors changes and then all the and then you have you have initial conditions and then a final condition, then you would choose to use the combined gas law to solve for whatever variable you are being asked to solve for. However, if you just have a sample of gas and there's no changes applied to it, right, you would then use the universal gas law. Once again, why? Because this has all four factors that pertain to a sample of gas: the pressure, the volume, the number of moles, and the temperature. Now, you guys, I will admit, I know I'm going really quick. I'm going to try to pick ones on the sheet that I'm going to give you just based on the ones that I think you guys can do based on the limited information that I've shared with you today. So we're going to do the best we can. All right, until next time, we'll see you guys.